our speakers. I hope we have all of our speakers. Let's get things rolling. So welcome everyone. Thank you for joining us for this Countdown to Mars, brought to you by STEM Rising, the U.S. Department of Energy's initiative sharing all things STEM across DOE and our 17 national labs. I'm Matt Dozier with the department's Office of Public Affairs. I host our podcast, Direct Current, which covers all kinds of exciting science stories like the one we're talking about today, which is the countdown to Mars. So this Thursday, February 18th, NASA is going to attempt to land the Perseverance rover on Mars to continue our exploration of the red planet. This is a thrilling moment for anyone interested in space exploration, especially our guests on the stream today, since they all played really important roles in developing and fueling the rover ahead of its mission. If you're following along, say hello in the chat and let us know where you're watching from. We'd love to hear from you. Without further ado, joining me today, we have a really incredible group of scientists from 3 different national laboratories across the US, starting with Los Alamos National Laboratory. We have Roger Wiens. Roger is a scientist at Los Alamos National Laboratory and principal investigator of ChemCam and SuperCam, laser spectroscopy instruments developed at Los Alamos for NASA's Curiosity and Perseverance rovers. We have Nina Lanza, who's also a scientist at LANL and a member of both the SuperCam and ChemCam teams. Hi, Nina. We have Jackie Lopez Barlow. She's the Radioisotopes Power System Program Manager at Los Alamos National Laboratory, which includes overseeing the development of the nuclear power source for the Mars Perseverance rover. We also have folks here from Oak Ridge National Laboratory, including Robert Wam, Program Manager for Plutonium-238 Supply Program at ORNL. Hi, Bob. We have Nydia Gallego. She's the senior R&D staff at Oak Ridge National Lab. She's the task manager for the production of carbon-bonded carbon fiber components within the Radioisotope Power Systems program. And we have George Ulrich. George is the program manager for Radioisotopes Power Systems program and group leader for Allied Behavior and Design Group at Oak Ridge National Lab. We also have Idaho National Lab represented here. Kelly, I see Kelly giving the thumbs up. Kelly's from INL's, she's the project manager for fueling, testing, and integrating ground operations for the multi-mission radioisotope thermoelectric generator, MMRTG, powering Mars Perseverance rover. We have Chris Browning, I think also there just off cam. Hi, Chris. Chris works as a technician in the Space Security Power Systems facility at Idaho National Laboratory. He has worked in the assembly, testing, and integration of radioisotope thermoelectric generators for Pluto New Horizons, Mars Science Laboratory, and now the Mars 2020 mission. We also have Shad Davis. Shad is a nuclear research facility engineer for the Radioisotope Power Systems program at Idaho National Laboratory. Davis was INL's Mars 2020 ground operations lead for the mission integration activities of the multi-mission radioisotope thermoelectric generator, MMRTG. How many more times should I try and read that whole acronym off? Anyway, welcome everybody. Thank you so much for joining us for the Countdown to Mars. It's a really exciting week, obviously, and I can't wait to talk to all of our scientists we have here on the call. We're going to just dive in here and try and give everybody a chance to share a little bit about the work that they did contributing to this project. Now, starting off with very broad strokes, I want to ask, what is the mission to Mars? And so Nina Lanza, Los Alamos National Lab, if you want to chime in and let us know kind of what is this in broad terms?
Yes. So why are we going to Mars? Besides the fact that it's totally awesome and just great to go to another planet, we are actually trying to learn some very specific things. And so there are 4 main objectives of the Perseverance rover mission. The first one, of course, is to understand the geology. So looking at rocks, but we're really interested in specific things that geology can tell us, like habitability in the past. So habitability is an environment in which life as we understand it could have existed. So we're looking for these past environments that could have supported microbial life on Mars as recorded in the rocks. So we're looking for evidence of water, water-form minerals, and preserved organic materials. In addition to understanding geology, we're also going to be looking at the astrobiological potential of Mars. So we're looking for biosignatures. This is signs of past microbial life actually being on Mars. So this is really exciting. It's not just environments for life, but rather life itself. It could be something morphological, like a fossil, but it's probably going to be more likely something that will be chemical or mineralogical that we're looking for. But really exciting mission. And along with those two objectives, we'll also be supporting a future mission to return samples to Earth. So we'll be identifying samples that have good possibilities for biosignatures, and we're going to cache them for a future pickup by another spacecraft to bring it back to Earth to be able to analyze these materials in more detail in our laboratories. So this is really exciting. It's the first time we would have ever done sample return from Mars. So that is such an exciting part of the Perseverance mission. We're starting that first step. And then finally, we're trying to prepare for a future human mission to Mars. So of course, we're going to assess the current environmental conditions, but we're also going to be testing some technologies that might support our future astronauts. So one thing that we're doing is we're making oxygen on the surface as part of the MOXIE instrument. So we're trying to do that not only so our astronauts have something to breathe, but so they can have rocket fuel so they can come back as well. And we're also testing a helicopter, which will be the very first rotorcraft on Mars, which is really fun and exciting. And so we're going to use that as a scout. So we'll be testing all of those things in support of our future astronauts. So if you can move to the next slide, I just want to show you an image of our landing site. So this is a close-up of a crater called Jezero. So you can see I've kind of put the dashed line on the right in sort of orange. That's the crater rim. So you can't see the full crater here. I just want to show you, though, the landing area has this incredible, what we would call a delta deposit. So I don't think you have to be a geologist to think, this kind of looks like water might have been here. And you would be right. So this forms when you have a stream flowing into a standing body of water like a lake. So we think that there was a lake here, a long-lasting lake that allowed for this delta to grow. And I'm showing a little inset of a delta in Alaska that kind of shows you what it looks like when it's actually being produced. Of course, on Earth, we have lots of vegetation. This is a great place to look for biosignatures. This is a great place for microbes to both live and also be preserved. So this is going to be a really exciting mission to actually look at what was probably a very habitable place on Mars in the past. And we're going to try to figure out if it was maybe inhabited.
Nina, thank you. So now the Department of Energy and our national labs were pretty integral in the execution of this mission. And so I want to go over to Kelly Lively at Idaho National Lab to talk a little bit about the way that the Department of Energy and our national labs were involved in getting this thing off the ground, on its way to Mars, and ready to search for ancient life.
Great, thanks, Matt. And I think we have some slides coming up. Good afternoon, everyone from Idaho. My name is Kelly Lively. I'm the Idaho National Laboratory Project Manager for Mars 2020. The Department of Energy has a national radioisotope power system programmatic mission to fuel, test, and deliver these nuclear power systems and related technologies for use in remote, harsh environments, such as space. So you see what Matt so eloquently repeated several times, the multi-mission radioisotope thermoelectric generator over there on the left side of your screen. And I'm just going to talk a little bit about the national program today. So what is a radioisotope power system? I do draw your attention to all of the pictures on this slide. The Perseverance rover uses an MMRTG. It's why we have acronyms, because we have really long names for things. And we use it to generate about 120 watts of electricity. The thermoelectric modules located within the power system housing use the temperature difference between the radioactive decay heat of its fuel and the coldness of space to generate direct current power. This 120 watts of electrical energy powers Perseverance's instrumentation and mobility. It's designed to provide power for a 14-year mission plus 3 years of storage before mission execution. The bare or unclad ceramic plutonium oxide fuel pellet is pictured in the small red cylinder pictured in the center of these pictures. The plutonium oxide pellet is fabricated and welded into its iridium cladding, creating the fueled clad pictured to the left of that pellet. It measures roughly 2 inches in diameter and 2 inches in height. 32 of the fueled clads are assembled into 8 general purpose heat sources, which are pictured on the bottom right. In turn, the 8 general purpose heat sources containing all of those 32 fueled clads are really the heartbeat of what we do here at the INL. We place those general purpose heat sources into a stack, and then we slowly insert that stack into the central cavity of the MMRTG, providing the heat to the thermoelectric modules, which is then converted into electricity. Next slide, please. RTGs have successfully been used on 27 missions since the inception of the program in 1961. Here at the INL, we have been involved in 3 missions, New Horizons, the Curiosity rover, and now Mars 2020. And on behalf of the Department of Energy, 3 of its 17 national laboratories are responsible for providing the MMRTG that powers NASA's Perseverance rover. Oak Ridge National Laboratory, located in Tennessee, produces plutonium-238 isotope and performs fuel-clad component manufacturing and testing to power tomorrow's NASA missions. And you're going to hear from them today as well. Los Alamos National Laboratory are located in New Mexico, and they process the plutonium into fuel pellets and encapsulate them into the iridium fuel clad. Idaho National Laboratory then is responsible for fueling, testing, delivery, and ground operations in support of mating the MMRTG to the rover at Kennedy Space Center, and finally at Cape Canaveral Air Force Station once the rover sits atop the rocket. So you're going to hear scientists, engineers, and technicians from all 3 of those laboratories today. Next slide, please. DOE's national laboratories tackle many challenges and possess unique instruments, facilities, and capabilities. And you're going to be hearing directly from a few of the scientists, engineers, and technicians and professionals from these national laboratories as they communicate how they're contributing to the RPS program. Bob Wam from Oak Ridge National Laboratory will start us off with DOE's radioisotope power system production flow. And each presenter will be describing technical capabilities and sharing personal thoughts and experiences in our endeavor to enable deep space exploration. And we're so proud to be able to present this information to you today, and certainly happy to be just a little part of history.
Thank you, Kelly. Let's with that go over to Bob Wam at Oak Ridge National Lab, and I want to hear more about the fuel that is keeping this rover running. Bob, if you wouldn't mind giving us a little primer on plutonium-238.
Okay, plutonium-238 is a unique isotope of plutonium, and what's unique about it is the way it decays. It decays principally by alpha emission, and it gives off a lot of heat. The key part of it is it gives off a lot of heat, and it's got about a 90-year half-life. So that means about half of it will be around 90 years from now. So it gives off a fairly constant amount of heat that can be used to, as Kelly described before, be converted into power and then can provide electricity and power to the rover. We get the feedstock from the Idaho National Lab, and the feedstock is called neptunium-237, and we take the neptunium-237 and process it into small pellets, which are then assembled into a target that goes into the high flux isotope reactor, which is also at the Oak Ridge National Laboratory. Once that material is irradiated for roughly 2.5–3 months, it comes out of the reactor and we allow it to cool. We then move it over to one of our hot cell facilities, put it inside that facility, and do a series of wet chemical processing steps in order to separate the plutonium from the neptunium and from fission products that are generated during irradiation. Once we've cleaned the plutonium up, we then convert it back into a solid material, package it, and ship it to to Jackie Lopez Barlow out at Los Alamos National Lab.
So it has a long road to go before it even gets in the spacecraft,
Yes.
or did, since it's now on the spacecraft heading towards Mars. We are going to go through that path and trace it a little bit. But before we do, I want to hear a little bit more from Los Alamos about the other half of the National Lab's contribution to this effort. And that's what is going to happen once Perseverance touches down on Mars. Roger Wiens, would you mind giving us a little intro to the work that your team has done on the SuperCam and what that does?
Sure, I'd love to. Can you hear me okay?
We can.
Great. Yeah, so we were picked to lead this, well, we put in a proposal, I should say, for this invention called SuperCam. And this is the remote sensing aspect of this rover. And so SuperCam's mast unit part sits right on the top of the rover and looks out with this big 4-inch diameter eye at everything. That is our telescope. And it's the only telescope besides ChemCam, which is like it, on the surface of Mars. So let's advance to the next slide. SuperCam has a lot of different things that it actually does, all in one instrument. So here we have just a picture of the laser beams in the upper left. It has both an infrared and a green laser beam, and it uses that for different techniques. So on the lower left, you see that it has this flash. Basically, it creates a spark with this laser pulse of infrared YAG laser, and that gives us the elemental composition through a technique we call LIBS. And we've done that on ChemCam as well on the Curiosity rover. So we're using the same package, but packing a whole lot more into it this time. Now on the right, I think there's a series of slides. So if you can go to the next one, there you see a target, and in the next one, you'll see a bright, brilliant green beam there, and you can actually toggle those back and forth to show a little bit what it looks like. And that's a sample that's inside of a chamber, in this case on the right. But whoops. So if you can go back, those are the two techniques that use the laser. We also use an infrared spectrometer to do more mineral detection besides the Raman, the green laser Raman spectroscopy. So those three techniques are all spectral techniques, and then we get imaging and sound. So I'm going to go to the next slide here, just to point out that SuperCam has a microphone, and that's circled in the lower part of the image here. And so you can see that microphone is sticking out. You'll see the inside of what's surrounded by a white box on the top of the rover. But then the microphone is on the outside. And that's so it can hear the sounds. And we can actually point that mast in different directions. So it's a directional microphone. It's a scientific microphone in that we have many scientific purposes for it. One is to listen to the zapping sound of this laser beam, and by actually hearing that sound, we can distinguish whether the rock is hard or soft and whether it has a coating on it from weathering or not. So that's pretty cool. And then we can also listen to the wind and get the wind direction and the wind speed from that microphone. Very useful little instrument in a part of SuperCam. Next slide. We also have very high resolution imaging that we take through this telescope. And so you can see this tiny little sub-millimeter laser pit in these blown up images from the SuperCam remote micro imager. So you could see a human hair on the ground looking all the way down from eye level. So this is also to support where we're actually making these measurements. That's very important. So next slide. This just shows the cover of our proposal. It shows that we have all of these different techniques at our disposal as basically a geologic observatory on the top of this rover. And we're so proud to be able to do this as a part of the DOE and Los Alamos. Back to you.
Really incredible capabilities that SuperCam offers. I think we're all really excited to see, knock on wood, what it does once it lands on the surface of Mars. But without a power source, SuperCam wouldn't be much use. So I said we would go back to the plutonium-238 and the fuel source that powers the rover. So I'm going to go over to George Ulrich at Oak Ridge National Lab, and I want to follow, if we can, the path of this step by step of this fuel that's going to eventually make its way into the rover. So George, can you tell us a little bit about your piece of this puzzle?
Yeah, Bob, Wam already told you about the PU-238. PU-238 is long-lived. We've got long mission. And so the fuel is hot. And so we at Oak Ridge also make the primary containment material for the plutonium-238, the stuff that actually holds the fuel pellet and is compatible with it. And so temperatures we're talking about are anywhere from 600 to 1,000 degrees C. And so it's got to get along with that plutonium as well as the graphite components on the outside. And so iridium is the most corrosion resistant metal. It's a high melting point metal around 2,450 degrees C. And then so we make that containment material, the pellets, and we make the alloy itself. We add parts per million quantities of materials to enhance that iridium. So we add thorium and tungsten and aluminum. And those alloys, the main one, the thorium, adds high temperature impact ductility just in case during a possible launch accident, which thankfully there was none of that. But that's the purpose of the iridium. We make those sets, they're called clad vent sets, to 2 sets of cups. We ship them to Los Alamos, and Jackie Lopez and Barlow and Company do the welding of those compounds.
So before we leave Oak Ridge, actually, I want to touch on another aspect of the safety and ensuring it, and I want to kick it to Nidia Gallego. And Nidia, do you want to weigh in and talk about carbon-bonded carbon fiber and tell us what that's all about?
Yes, I'll be happy to. So I'm Nidia Gallego. I work under the team with George Ulrich and everybody here at Oak Ridge. My role is to produce the carbon bonded carbon fiber, or CBCF. That's an acronym. This is a material. It's a very low density, lightweight insulator, meaning low thermal conductivity material. As George and Bob have mentioned, we have the plutonium is very hot. It's encapsulated in the iridium. We need to make sure that the iridium stays at the correct temperature to be able to protect the plutonium. So the insulator secures that heat and maintains the temperature. It also helps maintain the heat losses from the plutonium to a minimum so that we can maximize the use of that heat for the production of electricity. The production, again, this is used by mixing carbon fibers with a phenolic resin and molding and then machining this. Our machinist is very qualified. He actually described this as machining graham crackers because this is a very porous material. It's about 90% porosity. It has to be machined to very high standards and very precision so that it fits perfectly once we ship everything to Idaho and then assemble everything. So our qualification process is very strict. That's it. That's a small piece of the puzzle that we help to put together this mission.
Right, but even for a small piece, I mean, there's such exacting specifications and testing going into it.
Correct.
Before we follow the fuel sources journey from Oak Ridge to Los Alamos, I want to give a shout out to the folks who are watching. Thank you so much for joining us on this countdown to Mars. Say if you're watching where you're from in the chat. I see folks from Santa Fe, Louisville, Tennessee, Calgary, Canada, Nashville, Fairbanks, Alaska. We've got a great group of folks watching. Thanks so much. Sound off in the chat. And if you have questions for our experts, you have questions about getting into STEM education, STEM fields, feel free to drop those in there as well. We've got folks monitoring the chat. And we're going to get to some questions later on. With that, we're going to follow the next step in the plutonium-238's journey over to Los Alamos National Laboratory. Jackie Lopez Barlow, a couple of folks have mentioned you by name. You're on the receiving end of this this shipment of plutonium, right?
Yes. Everybody, nice to see you, and thank you. Yes, but we do we're the ones who pull everything together to make the plutonium-238 fuel clad, which gets assembled at Idaho National Laboratory into the general purpose heat source modules that Kelly was mentioning. So our job is to get all of the nuclear and non-nuclear components for the fuel clad and to ultimately make one unit that is ready and flight quality and safe to be able to be launched. So the way we do that is we get the plutonium-238 oxide and we take it through our aqueous process, where we remove all the impurities so that way we have really good clean fuel. Then we'll take that material and we'll do some furnace operations to prepare what we call the fuel, the heat source fuel. And we ultimately land up hot pressing a ceramic Pu-238 pellet. And so if you can imagine a coffee cup, that is what our pellet eventually looks like after build, and how hard it is after we've done the pressing and the sintering of it. And so then we take that ceramic pellet and we put it into the iridium fuel clad that we get from George's team that they've so graciously manufactured for us. So we then have this clad, it's in iridium, and we will then go and take it through various stages of non-destructive testing. So we make sure that our weld is inspected. That is a huge safety aspect of our fuel capsule, to make sure that it is going to survive and it's going to do what we need it to do. We also want to make sure that we understand how much power are we going to be providing from our different fuel capsules. So we work with Idaho National Laboratory on that to make sure that our fuel capsules meet the requirements for the overall MMRTG power output. And so we get that information, and ultimately we create once we're done with all the non-destructive testing, we then can ship all of our clads over to Idaho so they can get assembled. In addition to that, we also do safety testing to make sure that we can stand behind and all our design and our safety features that have been put into this. So it's a great process because we get to work with Oak Ridge, we get to work with Idaho, we blend it all together, and we come out with a product that can power the MMRTG, and like Roger mentioned and Nina mentioned, our awesome instruments on the Rover.
Awesome. And if you've been watching since 3 o'clock, you may have started to get the sense of just how much coordination, communication, collaboration is involved in this whole process. So from Los Alamos National Lab here, we're going to head over to Idaho National Lab, where Chris Browning, I think Chris has now taken the place of Kelly on screen. Chris, what do you do with the fuel clads once they arrive there in Idaho?
Okay, well, hello, my name is Chris Browning, and I'm a nuclear technician here at the Idaho National Laboratory. With our team, we have about 70 people. We have engineers, technicians, quality assurance, and of course, administrative staff. Our team is responsible for assembling the Pu-238 into the modules. We use a lot of acronyms, right? But we'll just kind of size it up. Basically, we're going to take the PU-238, and I've got some simulants here. Let me just show you kind of what it is. This is kind of roughly the size of it. This is just a simulant that we use for display and training, that sort of thing. And we assemble the heat sources into the modules. Basically what it is it's a graphitic block that you've heard folks talk about. This gives you an idea of the relative size of these things. And we're going to put 8 of these modules together, and that'll be a fuel generator. What's really interesting about our generator is there's no moving parts. It's all done through heat, which is pretty remarkable, really. So once we get the assembly of the generator done, then we're going to move into the vibration testing. And if you bring up the slide of the MMRTG workflow, please. Okay, there we go. Great. Okay, we'll start with the vibration testing. So the object of the vibration test is we're going to mimic the levels of vibration that the rocket goes through upon launch and flight. And this test is to ensure that the generator produces the necessary power output through the vibration before and after the testing. Okay, the next test that we're going to run through is going to be mass properties. And that's the 4th picture over on the right. You can see the generator kind of at a horizontal. There you go. The object of the mass properties is what we're going to do is we're going to weigh that generator, and we're going to find the center of gravity. And with that, we're going to forward that information to the Mars 2020 and the Mars Perseverance rover teams. And then in turn, they'll use that information to make their overall launch calculations and then different aspects in the flight as well. Okay, the final test that we're going to do here in Idaho, at the Idaho Laboratory, is going to be thermal vacuum testing. And that's going to be that big orange chamber on the right side. What that is it's a very large vacuum chamber. And essentially what we're going to do is we're going to place the generator in a vacuum to simulate a space environment. And what that's going to do is it's going to tell us, ensures the generator is going to operate in space without a decrease in power. And really that's the really important test for us, is to see how this thing's going to perform in space and of course in the Martian atmosphere. And then from there, we go to the transportation aspects. And then one of my coworkers, Shad, will talk about that one.
Yeah, absolutely. And so this thing is tested within an inch of its life. You've got to make sure that it works because NASA's counting on this. NASA's counting on this thing to work, or the whole thing is kaput pretty much, right?
Absolutely. There's no redos. We can't bring it back and fix it. Everything's got to be right the first time.
Right. So, Shad, if you want to jump in and talk a little bit about what it's like handing this thing off to NASA, because that's its own challenge, I'm sure.
Absolutely. As Chris alluded to, our successful completion of our acceptance testing, our job at INL is not done. We have to get this thing down to Florida and up and made it to the rover and onto the rocket. And so that's where my job came in. I was the ground operations lead, coordinating those activities down in Florida to make sure that we could get the generator where it needed to go. So the MMRTG for the Mars Perseverance rover was packaged and shipped in late March of last year. And at that same time, a team of about 25 folks from INL were assembled, and we all traveled down to Florida to support and conduct those operations. And in the time of COVID, that travel was quite a challenge in and of itself. And we were successful in getting everyone down there and in place to support these operations for this critical mission. For those of you that have never been to Florida in the springtime, it's a beautiful time to be down there. Unfortunately, in the area we were at, it's home to these biting bugs called no-see-ums. So if nobody's ever experienced those, I had never experienced them, but they are a vicious creature. And so that was a challenge, just dealing with those things outside of our work environment. But so it wasn't an all pleasant experience. But my personal pain aside, our first key milestone was the integration ops involving the Jet Propulsion Laboratory. And the first aspect of that was conducting what was called a hot fit check. This was a key component, a key operation done. It was essential and exciting for everyone involved because this is the very first time that a nuclear powered RTG has made it up to the rover. And so our responsibility was to deliver the MMRTG to the Payload Hazardous Servicing Facility where this operation was conducted. This is a huge facility where JPL and NASA has all of their spacecraft equipment, and the rover's there. They've undergone several testing with the rover. And so we are there to support the electrical and mechanical mating of the MMRTG to the rover. Subsequent to that, the JPL team conducts a series of functional and power tests involving the rover and the RTG mated to it. And it's just an assurance that the rover is going to function with the nuclear power source hooked to it prior to launch. Following that, there's about a 3-month lag between that operation and launch. And so the RTG is staged and stored at a nuclear facility that we've established down at the Kennedy Space Center in Florida. And so we provide support and oversight and monitoring of the RTG while it's in that staging stored position. About 10 days prior to launch, our crew is back down there to perform the final integration of the MMRTG to the Mars rover. So we deliver the MMRTG to what's called the Vertical Integration Facility. This facility is located on Cape Canaveral Air Force Station. This is the location where the Atlas V rocket is assembled. The payload fairing is hoisted up on top of the rocket, and the Mars Perseverance rover, all bundled up inside of its aeroshell, mated to the descent stage and cruise stage, is all assembled. And so the last key piece of that is our RTG that we deliver. So our team hoists this little generator 170 feet up into the air at this facility using a 65-ton crane. So it's quite a sight to see this huge crane hoisting this little RTG. It's actually in another container, but right up alongside this 200-foot tall Atlas V rocket. But it's a very tense and scary moment. The worst possibilities that run through your head at that moment, I'm thinking, please don't drop, please don't drop. And, knowing very well that likelihood is slim to none. But so we're there to support that final integration of the RTG to the Mars rover. And at that point, we all bid our farewell to the RTG as it's secured to the rover, and the aeroshell door and the payload fairing door is all buttoned up and awaiting to roll out to the launch pad. And up to that launch, our operations are complete for this mission.
What was it like watching the launch?
It was incredible. It was absolutely incredible to see that and know that you had a small piece to play in that mission, sitting on that rocket flying up through space. It was you can't explain it in words. It was a once in a lifetime experience.
Feelings that I know are shared by a lot of the people on this call. Thank you, Shad. Appreciate that. We have a question for the audience here. Since this is a STEM-focused stream, what STEM field do you most want to work in? So if you're in the chat, you're watching along, let us know what STEM field you most want to work in. Also, thank you for those who have shared their location. I see Elizabeth in South Carolina saying no CMs are ubiquitous there too. We've got Wendy from Idaho National Lab, Jason from New York City, Emma from Michigan, Teresa Johnson from San Francisco, California, Amanda from Colorado, really all over the place. So thanks for joining in and watching along. Want to talk a little bit more about the way that DOE and the national labs have been involved in this mission, because NASA obviously has the lead on this project. They do incredible work, and I'm sure a lot of people are curious why the Department of Energy is involved. Bob Wam at Oak Ridge National Lab, I want to go back to you and talk a little bit about what DOE and the national labs can offer that that NASA needs assistance with.
Well, okay, the one big thing that we have, and again we have it at the Oak Ridge National Lab, as well as there's a research reactor at the Oak Ridge National Lab. There's also a research reactor at the Idaho National Lab, and both of those are key to transforming the neptunium into plutonium. We have some hot cell facilities at the Oak Ridge National Lab, which is A hot cell, if you think of a laboratory fume hood in your typical chemistry lab, imagine something that size, but now is surrounded by 4.5 feet of concrete. And you do your work remotely. It's a unique facility. It's been making radioisotopes for DOE for about 50 years. So it's been a key contributor to the DOE radioisotope program for a long time. And then most recently, since about, I guess we made the first significant quantities of plutonium-238 in 2015. So we were able to make that material, ship it to Jackie, so that Jackie would be able to take a look at it and see how it would work with their system, and it worked well. So.
Roger, over at Los Alamos, what was it like working with NASA to develop these instruments? Because you've worked with them on past missions as well. So, how has Los Alamos kind of been involved on the instrument development side that, gives NASA sort of an additional boost?
Yeah, Matt, thanks for asking. There's one slide here that just talks about sort of LANL's historic perspective in space. Basically, in 1963, President Kennedy picked the Los Alamos Lab to help to verify the enforcement of the Nuclear Test Ban Treaty in space. That is, that no nukes are being set off in space. And so that set us, this lab, before my time, on a course to working on spacecraft instruments. And so there's been sort of a parallel path where Los Alamos in the ISR division has worked on both NASA instruments and instruments for these enforcement of no nukes in space and other things. So that's really where we got started, and we've done a lot of great NASA projects over the last number of years, some including neutron spectrometers or gamma ray spectrometers, which have dual use here at the lab as well. And then more recently getting involved in things like this LIBS technique, and then branching to others. And so we've just had a really great time. As I show here in this picture, we were involved in the Curiosity rover, and I wrote about it in my book, Red Rover. And so we have a great history.
Thanks, Roger. Kelly, kicking it to you real quick. So, Idaho National Lab's perspective, what kind of work does the lab there do that gives, additional capabilities to what NASA offers?
So the radioisotope power system program was moved from Miamisburg, Ohio, back in 2002 to this lab. So hence we've not been involved in it for as long as the program has been established. But we are certainly enjoying our contribution at this point. But we're involved as a contributor under the Department of Energy, under the Code of Federal Regulations. So there is a register of federal rules that govern the handling of nuclear material, and so that's what gives us our authority and to do what we do. But certainly our capabilities here, we have a nuclear facility that we work in and that we abide by those rules in handling our nuclear material. We also use the Advanced Test Reactor, shout out to them, here at Idaho National Laboratory to irradiate those targets, as well as the HYPER reactor at Oak Ridge National Laboratory that Bob Wong was talking about. So we also have another nuclear facility where that neptunium is stored that Bob spoke of, which starts out the supply of producing the plutonium-238. So we have several nuclear facilities here, and then we take our management skills on the road down to Kennedy Space Center and Cape Canaveral Air Force stations, and we actually declare facilities there, nuclear facilities, and we have to abide by those Code of Federal Regulation rules in those remote places too when we're handling all this radioactive material.
Thanks, Kelly. So the question we put out earlier, what STEM field would you most like to work in? We've got some answers coming in. We have planetary science, astronautical engineering. Jeff says chemical engineering. We've got robotics, cybersecurity, geology, non-terrestrial officer. There's so many different ways that folks can get involved in space exploration, and these are just a few of the examples of that. On that note, I want to ask some of our guests about their STEM education and how it played a role in their careers and leading them to this work. Nydia at RNL, would you like to share some of your experiences regarding your STEM education?
Yes, so my background is in material science and engineering, and I'm a little biased. I mean, there's materials in everything. I mean, we, on a daily life and everything we do, we had to deal with materials. So in material science and engineering deals with understanding how the structure and composition of the materials affect the properties. So we are on continuously, my work on a daily basis, we are working with developing and processing materials, making sure that they meet the standards, that the properties that we're looking for ways to improve those properties. As I said before, on this CVCF, we want to make sure that the density, that the thermal conductivity, that the strength, the materials are the ones, the minimum requirements, and always working on different ways to improve those materials.
Thank you. Shad, at INL, did you ever think, that your education would lead you to this point that you were at, watching the RTG be hoisted up the side of a rocket?
No, actually, it's pretty ironic. My background is in mechanical engineering, and I took one nuclear engineering course in my entire life of my education, and never would have dreamed I would have been working in the nuclear field. And I actually started out at Los Alamos National Laboratory on the plutonium fuel capsule side of the house back in 2002. And throughout the almost 20 plus years I've been involved in mechanical engineering, I would have never dreamed that I would have been part of what I was a part of last July to send something now going to be landing at Mars in just a couple days.
You really never know where these educational opportunities can lead you. So worth taking that one course in nuclear engineering.
Yes, it was. It's paid dividends.
Nina at Los Alamos, how about you? Tell us a little bit about your background and how it led you here.
Well, sure. I mean, I've always been obsessed with space and spaceships. So I really wanted to do work like this. I had no idea how to do that. I figured, though, I should probably major in astronomy because that's how you study space, right? And it was only right at the end of my undergraduate career that I realized that planets like Mars are made out of rocks, and I need to know something about rocks if I want to study them. So having never taken geology as an undergraduate, I actually went to graduate school in geology. And so now I can actually study the surface of Mars. Who knew? So I've been really happy to be able to take, my enthusiasm for this work and actually channel it into something where I can actually contribute, which is something, I think that's like living the dream, right? I'm living my childhood dream of working on a spaceship on Mars with lasers. That's awesome. But I had no idea how I was going to get there. I think essentially, you just have to find the place where you're most comfortable, with the subject. And go from there, because as you can hear, everybody here has such a different background, right? There's all kinds of different expertises here. So you don't have to pick one to be able to be involved.
Right, absolutely. We have Laura in the chat saying rocks rock. So you've got some geology fans with you. Thanks, Nina. We have another audience poll here, different question for folks watching along. What is the most surprising thing you've learned so far in this event? Throw your answers in the chat and we'll get to some of those later. While you're doing that, I want to move along and ask some of our other folks on the call what advice they have for attendees who are watching along that want to pursue STEM careers. And Jackie at Los Alamos, I'm going to start with you. What advice do you have for potential STEM majors, STEM professionals?
The advice I would give is never stop asking questions. That's one thing that's so cool about STEM degrees and fields is it's our job to find solutions to some of these challenges. Nothing is known So it's our job to go find the unknown. So constantly ask questions and pull that string, dig a little deeper, because you're going to find something new. And when you do, it's awesome. You're adding that piece to the unknown, and now it's known. So constantly ask questions.
That's great advice. Chris Browning at Idaho National Lab, what advice would you give to somebody who's interested in doing a career in STEM?
Well, Matt, I would encourage them to be bold and ask for opportunities. You can't be told no if you don't ask, right? So then I would take advantage of the opportunities you're given, internships, jobs, and then take assignments that you normally wouldn't take or maybe not thoroughly be interested in, but it does pay dividends, as Shad mentioned. It worked out very well for him. You don't have to be a 4.0 student. Of course that helps, but you do have to believe in yourself. Probably learn to communicate with folks, learn how to collaborate with others. And to sum it up, I would say educate, communicate, and collaborate.
Those are all essential to the work that you all do. Absolutely. So good advice for folks at any stage of their career or education. George Ulrich, we haven't heard from you in a bit. What do you got in terms of advice for folks wanting to pursue STEM careers?
Yeah, it's be willing to dream, be open. I grew up watching the early space program from Mercury, Gemini, Apollo, and then the space shuttle. And I had, I actually, when I was little, wanted to be an astronaut, but I knew that, I was good at, and I liked math and science. But when it came time to, high school, college, decide on a specific major, I wasn't sure of what it would be. And, early on, it was not going to be, I didn't know what a metallurgical engineer was. But that's what I ended up doing, getting involved with materials. But the world's your oyster. From mechanical to chemical to nuclear to materials, aerospace, systems designer, whatever. The name of the game is figure out what you like, what lights you up, and be willing to go for it, and willing to collaborate with people all over the world, all over the US, all over the world. And you're unlimited. So dream your dream.
I think it takes big dreams to do this kind of work, to come up with spacecraft that are headed to other planets, to create the tools, the fuel sources, involving all these different people and all of these different disciplines. You really have to have a big imagination. So thanks, George. We have a couple of answers to our last question. We have Tan Whitcomb saying that machining CBCF is like machining graham crackers. Yeah, I thought that was pretty surprising as well. Lakeisha Walker says the lake image from Mars was very eye-opening. I agree, the Delta view was really cool. And Laura Crossie saying the information about the complexities of the power supply is fascinating. So thanks for everyone who's been watching along with our countdown to Mars. And again, that's coming up on Thursday. We have, I think, some audience questions. And if Anne-Marie from Department of Energy with STEM Rising wants to chime in, that would be awesome.
Hey guys, so I'm Anne-Marie Horowitz. I run the STEM Rising effort at the Department of Energy. It's a project of our public affairs team, so you can find it on energy.gov/STEM. I wanted to thank everyone on the line for attending, and especially our panelists. So these guys are for you. I think this first one from Jesse caught my eye. They said part of the mission was to search for life on Mars, as Nina outlined in her opening remarks. And Jesse was wondering if the RTG has sufficient shielding to prevent it from affecting any potential life that could be found. So I think Nina will ask that for you.
Oh, sure. Yeah. So I probably wasn't very clear. We're actually looking for ancient life. And so we don't really have the tools to look for extant life on Mars. I know that sounds crazy, but it's a really different set of questions that we have to ask. So we're actually asking, was there life on Mars? Now, that being said, you might think that the RTG isn't really very good for microbes today either. But you have to remember, there's no magnetic field on Mars already. So the surface environment in terms of radiation is not super friendly already. So any Martians that are already on the surface are probably very used to that kind of environment, I'd say. And also, that being said, we have microbes on Earth that can live inside nuclear reactors, which is insane, but life finds a way. So I would say probably, if we were worried about Martians, we probably don't have to worry about that aspect.
And I don't think we're worried about taking no-see-ums to Mars either, as somebody else asked in the chat. Thanks, Nina. Anne-Marie, is there another one from the chat you want to share?
Absolutely. All right. So Jason was asking, and this could be for anyone who's maybe experienced this, one of our panelists, for advice on those who want to change careers to STEM kind of later in life.
Yeah, anyone who wants to chime in on that, please feel free to unmute yourself. I see Kelly shifting into position.
I'm your poster child for later in life. So I was out of high school 10 years before I decided to start my academic career beyond that. And I was going to go into nuclear engineering and ended up, I had been working for engineers, typing procedures for them. So that's how I got interested in engineering. Started into nuclear engineering and then ended up taking a class in electronics and decided, oh wait, this electricity makes much more sense to me. So I ended up with a general engineering degree with an emphasis in electrical engineering from a little tiny college at Idaho State University. When I got out of high school, I wanted to become a certified public accountant. I wanted to be the one doing your taxes and doing your bookwork for your company. But I just got interested working for Newport News Shipbuilding, who was refueling a reactor at the Naval Training Facility for the United States Navy. And it just was fascinating to me. So I did go into it pretty ignorantly. I had no idea so much math was involved when I went into engineering because I really didn't have a perception of what they actually did. But it was a lot of math. It turns out I was just fine with a lot of math and couldn't be more pleased. Coming out of college, just not knowing how I wanted to apply it, just really fortunate to, as Chris had stated earlier, just look for opportunities and never say no to assignments. You're always going to learn something. If you're not making mistakes, you're not learning.
Yeah, that's great advice. Thank you, Kelly, for sharing. Anybody else wanted to weigh in on that? Because I do think we have one other question from the chat. All right, Anne-Marie, what do we got?
All right, so this one is for our Oak Ridge team. Megan, who is a journalist on the line, wants to know a little bit more about Oak Ridge's role. So I know we talked about it throughout, but if someone wants to give us a nice little nutshell encapsulation of that, perhaps that could go to George for a first pass.
What was the Oak Ridge role? Well, it's actually multiple roles, as you know, as you've listened here. Starts with Bob Wam and with the reactor work with the Neptunium-237 to make the plutonium-238. Then Bob's got to do a lot of chemical processing work to get the isotope, get the purity that's needed. So that is, it's done at Oak Ridge. It'll also be done at Idaho with the ATR. But then other parts of Oak Ridge, all these national labs are large facilities, a lot of people. a lot of diverse backgrounds and expertise. So, I mean, at Oak Ridge, we're talking over 5,000 people, about 5,500 people. So you've got the reactor aspect, the chemical processing aspect, but then my work and Nydia's work, we focus on the materials processing, materials characterization, Nydia with graphitics and carbon materials, so the making of the carbon bonded carbon fiber, and then with making clad vent sets. We make those cups, but we start with powder, pure iridium powder, a precious metal, which it's not preferred, it's not what you'd call normal, but it's very specialized, very unique in its capabilities. We start with this powder, and then that processing, the alloy was developed at Oak Ridge. It's called Dope 26. So it's got these parts per million levels of dopants that have been added to it. But the process to make the alloy, just the raw material, is a 9-month process. And then it's 4 to 6 months to make these clad vent sets that we end up shipping to Los Alamos, and Los Alamos does the encapsulation. So Oak Ridge, and then we're also involved with some involvement with some of the thermoelectrics, evaluating those, and these are the materials that heat, the decay heat, and then the cold of space. You got a delta T, a difference in temperature, and then these thermoelectric materials are made of dissimilar materials. So it's that temperature and the dissimilar materials we were getting electrical production.
George, can I jump in here real quick? I want to just say that I think that George's answer gets to the point of this entire stream, which is that there are a lot of moving parts at every single one of the national labs involved in this. It's an incredible feat of collaboration and coordination. And I think that if folks are watching and that are interested in catching something they might have missed, a lot of stuff got covered in detail regarding the different labs roles early on. So you can go to energy.gov/STEM to watch the replay of that after the stream once it's been uploaded. But we're coming up on our time here, so I just wanted to say thank you to everyone for watching this Countdown to Mars live stream today, to our guests, to the Lannel Foundation for facilitating the event, and to NASA for helping spread the word. You can find a recording, again, like I said, at energy.gov/STEM. And if you want an even deeper dive into the Mars Perseverance mission, you can head to energy.gov/podcast and listen to Direct Current's 2-part series on the Energy Department's contributions to the rover, which featured many of the faces and, well, just the voices of the folks that you've heard from here today. So again, thank you all for watching. We really appreciate you joining us here. And don't forget to tune in this Thursday, February 18th, to watch the landing live on nasa.gov. I think we're all holding our breath in great anticipation. So thanks everybody for joining us. Take care.